So I wanted to go through a few of Jerry's papers. And when I say Jerry's papers, I want to be very specific. I'm just going to show you. When I say Jerry's papers, I mean, oh, look at this. These are all scientific papers. They're most of them are math related. And I want to show a few of them to give the channel an idea of what it is that I have when it comes to these. Now, let's see. At one point, I know I organized these. I don't know if they're still organized. I think I organized them by date, and instead of by topic, because topic, I don't know enough about these fields to be able to organize these by topic, but date is pretty easy. They're pretty much all dated. So let's see. This right here is on crystal stability, and it is off-printed from the Discussions of the Faraday Society, 1965, number 40. 3 atom and 3 ion interactions and crystal stability. Not going to read the whole thing, just going to kind of go through maybe the abstract and a little bit of the, like, here's an article. It's an article. Here's the back where they have all the citations and everything. Here's the information. 3 atom and 3 ion interactions and crystal stability by L. Jansen and E. Lombardi, asterisk, on leave of absence from the Institute of Industrial Chemistry, Polytechnic Institute, Milan, Italy. International Division, Battelle Memorial Institute, Geneva, Switzerland. And a reminder, this is all from the collection of Jerry Silverman, and he was in Switzerland for a good period of his life. So this is like, whenever he has stuff, often it's because he was there. Observed stability of crystal structures for rare gas atoms and the isoelectronic series alkali halides. Group 2,6 and 3,5 compounds is correlated with atomic and ionic interactions in dense media. On the basis of central forces, essential discrepancies between theory and experiment appear. Further analysis indicates that strong simultaneous interactions between 3 atoms or 3 ions of short range play an important role in determining the stable crystal structure. An evaluation of such 3-body interactions is carried out in first and second orders of perturbation theory using effective electron wave functions of Gaussian form. It is shown that the theory accounts for all observed stability relations on a quantitative basis. The stability of the face-centered cubic configuration for solids of heavy rare gases is explained. Also, the occurrence of the cesium chloride structure for some of the heavy alkali halides and the magnitude of observed transition pressures are reproduced by the theory. In addition, it is shown that 3 ion interactions are responsible for the occurrence of the sphalerite and wurtzite configurations with the group 2,6 and 3,5 compounds without involving covalent bonding between the ions, permitting a quantitative distinction between these 2 types of structure. Hope you got all that in one sitting. I'm not repeating it. Rewind the video. So this one here, after that it goes into the math. I don't know enough about this to tell you much about it, but I will let you see a couple of the pages. You can always, freeze frame if you want to take a look at the details. A lot of Jerry's papers involve this kind of stuff. Crystal matrices, 2 atom and 3 atom, 2 ion and 3 ion interactions, and doing the calculations involved. So, Discussions of the Faraday Society, 1965. That's the first one of these that you've seen. I'm just going to go stick that. Let's see. How far back does his stuff go? I think probably, I've got like a little organization system right here, so I'm trying to think out loud. I'm going to say let's start at the 30s, since that's I don't have anything of his from the 30s. I'm going to start at the 40s. 40, 50, 60. So 60s would go right here. You're organizing this with me. Thanks for helping. So let's take a look at this big thing right here from a different stack. This is from... Okay, so let me show you the whole thing so you get a look at it too. This one has this one's a little bit more complex, as you can see. It's got like a slip cover or a cover on top that has a little window, and then there's like all the stuff on the inside. And as you can also see, there's corrections. Oh, it's not that it's corrections. The way that this was printed, still don't see a date yet, by the way. But the way that this was printed, it was like they had typed it out and then written in the stuff they didn't have characters for on the typewriter, which I see a lot of in these articles. I mean, I used to do web stuff for a research university, and a lot of the problems that we were hearing about were the inability to display their math on a web page. It's really hard to get all of those symbols to line up exactly how you want to in live text. And apparently it's always been a problem, because here we've got them writing it down. On the web pages, people would like make a JPEG or something and kind of put it right in the middle of the text. So that's exactly what this is. Now, as for what is it on? Intensive Observables in Quantum Theory. R.F. Streeter, Physics Department, Imperial College, London. Now, I'm having a bit of difficulty seeing the date here. Oh, there's an asterisk. Research reported in this document has been sponsored in part by the Air Force Office of Scientific Research, OAR, through the European Office Aerospace Research, United States Air Force. I think, I don't remember if Jerry was Air Force or no, he was Navy. So, but I mean, there's obviously, this is something that was sponsored by Air Force. It doesn't really, you can have that regardless. Now, this is blue pin here. So apparently this was printed and then they redacted it or something. I wonder who did that. I know I didn't, and I know that it came like this. So, yeah, there's some red pin corrections in here. Actual corrections. So, I wonder if this was... I wonder if this went to a journal or not. Or if, like, maybe it was a draft on the way to going to a journal. Really, really interesting. So, the paper is really thick and cottony, like letterhead paper. I wonder if that's one reason why these have lasted so long. Yeah, here's a little bit more of that kind of scratching out. So I guess that this whole section here has been determined to be it's a theorem 3. I guess theorem 3 has been struck from history. F theorem 3. So do we have a date on this? In the back, I have some stuff cited into the 60s, but no further than that. So my assumption is that this is another 60s document. It looks like it. So I'm going to stick it in the 60s for now. This one is on some nice magazine type paper. 2nd January 1967. That's when it was received. Chemical Physics Letters 1, 1967, 24 to 27. North Holland Publishing Company, Amsterdam. There's a little check mark on the top. I think that Jerry might have had a sorting system or something. I don't know if this was part of like how it came to him or what he did after looking through it. Because sometimes he marks it to show that there's something that is important. So it's like sometimes he's I think noting something about it. I'm just not quite sure what. Intermolecular interactions by perturbation theory, including exchange effects. A. van der Avoord. Asterisk. On leave of absence from Unilever Research Laboratories, Vlaardingen, the Netherlands. At the Battelle Institute Advanced Studies Center, Geneva, Switzerland. Another from the Battelle Institute. And another where someone's on a leave of absence from somewhere else to be at the Battelle Institute. That's interesting. A perturbation theory for intermolecular interactions is developed with wave functions of arbitrary symmetry. First and second order expressions are written out. For the sake of simplicity and practical calculations, the unsold approximation is introduced in the second order energy. So this one here is actually just one piece of paper, just folded in half. There's a bunch of Hamiltonians in here if you're into that sort of thing. And by the way, if you ever see one of these papers and you're interested in what's in it, I can provide scans if there are none available. I've heard that some of these papers have no digital versions available and are actually hard to get. And so, I mean, if someone needs it for science, surely for science, I'll help. Part of my curiosity has been like, you know, how much you can learn from these, because they were kind of just put in a box and forgotten. Physics Review 162, Volume 63, 1967. Note on a Schrödinger perturbation formalism for exchange interactions between atoms by Lawrence Janssen. Battelle Institute, Advanced Studies Center, Geneva, Switzerland. Noticing a trend. A Schrödinger perturbation expansion in first and second orders is developed for exchange interactions between atoms, starting from a complete orthonormal set of symmetrized, yeah, that's a real word, symmetrized basis functions. The results agree closely with those obtained by Eisenschitz and London for non-orthonormal functions, and with those derived from a Brillouin expansion. The evaluation of three-atom exchange interactions is discussed in the context of the different approximations used. So that's what's in there. So far, everything seems to be in the 60s. Curious if I can just grab something kind of random from the middle and see if we get anything different. Well, that's because the 60s is a giant stack. That would make sense. Let me grab another section underneath. See, I've got just so much of this. Glad to be putting in a better organization system. This is all temporary just to be able to keep it all in one place, but also separate out stuff in any way. See, this is another 60s. I think the problem is that that the 60s is like a foot tall, so I can't just put everything in the 60s. I don't know how I organized these in the first place. I'm probably going to have to go through all of them again. So I'm probably just going to go through them on the channel. I guess that's the plan. I'm just going to have to organize these on the channel, like either do live streams or record videos and post them. But yeah, I guess expect a lot of me looking through these type of videos because there's so many. I have hundreds of these and I just don't know how to index this information. Like, I'm probably going to have to catalog it in a Google Doc, in a spreadsheet, and start keeping up columns of what's important. Part of the reason why I haven't been doing that yet is because I needed to look through the material enough to become familiar with it enough to know what categories to put in a organizational document. You can't really index something until you know how you're going to index it, and then you can't know how you're going to index it until you understand the information and are familiar with it. So sometimes you just have to go through it several times until your brain kind of gets an idea of what the index needs to be shaped like, and that's what's been happening here. Because I do want to reach out to other people and say, hey, like, do you know what I could be doing with this? But I want to tell them what this is, and it's kind of hard to describe. I've got a big stack of papers. I don't know what's in them. There's Hamiltonians. There's a bunch of neutrons in here. So this one right here is from 1966, 8th of April. Reprint from American Journal of Physics, Volume 34, Number 10, 895 to 898, October 1966, printed in USA. By the way, this one is marked as a duplicate, which that's a lot of Jerry's stuff has it marked whether or not he has a duplicate, and sometimes I wonder if he had like a office copy and a home copy or something like that, or like was keeping track of two different offices or something. Maybe he had a copy that he would let people look at out on loan. But I don't think I've actually managed to find actual duplicate copies of articles in this whole stack. I think all of these are completely different from each other. So if there's another copy of this one, for instance, I don't know where it is. That didn't end up with me. Formulation of quantum mechanical perturbation theory. Edwin M. Roberts, Lockheed, Georgia Company, Marietta, Georgia. Wonder if that eventually becomes Lockheed Martin. Probably. There's a little pin mark here, 30060, so I think someone added a zip code after the fact. Don't know who. But a lot of the papers have like correspondence between Jerry and other people. Like he's kind of keeping up with friends while passing these back and forth. So some of it's just the ephemera of life. Abstract. A new expression is found for the perturbation energy with the principal feature that it is in remainder form. The remainder is first applied or manipulated to obtain the familiar infinite series of perturbation theory. Secondly, an iterative procedure for solving the Schrödinger equation is proposed. It is shown by making use of the remainder that this procedure leads to results equivalent in the small perturbation limit to the results of perturbation theory. And give you an idea of what this is all looking like. A little close up on the math there. This is another one that is just one sheet of paper. And at one point, this paper was white. It is like a sandy beige now. That's just, the effects of age on paper. Sometimes it's just amazing to look at this in terms of just the time it's experienced. So, yeah, I'm just gonna sort them by type at this point. If it's a little one-pager, I'll put it with all the other little one-pagers. Now I can... Yeah, it'll probably be easier to look through them if they just kind of stay similar. So I'll just do it like that. Just go by format. Like, it's really hard to organize stuff like this. There's no recipe for it that I know. I've never handled this kind of stuff, and I don't think most people will ever do. There are students, not students, but like I'm thinking graduate students, just people. There are academics who handle these quite often though. So, it's been kind of hard to imagine reaching out for assistance on this quite yet because life's been kind of crazy. I live in a house with no hot water, and I have for about 6 months now. And we don't know when that's going to end. So it's hard to organize all my physics articles that I have. I am not even a physicist. So, perturbation treatment of the ground state of HEH, helium hydrogen plus. Reprinted from the Journal of Chemical Physics, Volume 43, Number 4, 1101 to 1103, 15th of August, 1965, printed in the USA. Robert L. Macha, William D. Lyon, and Joseph O. Hirschfelder. University of Wisconsin Theoretical Chemistry Institute, Madison, Wisconsin. Received 7th of April, 1965. Rayleigh's Schrödinger perturbation calculations are carried out for the ground state of the helium hydrogen plus molecular ion. The zeroth order wave function is psi equals n exponent. Oh, a whole bunch of math. You read it yourself, honey. I'm not grown up enough for that one. There, I think. Can that be made out? You want it a little closer? There you go. It's all the math. The expectation value of the Hamiltonian calculated with the wave function accurate through first order E1 is compared with the accurate series calculations of Bates and Carson and found to agree up to 5 places. Also, the values of the normalized wave function accurate through the first order agree quite well with Bates and Carson, particularly for small values of the internuclear separation. So here's this. This is another one-pager. I'm going to put it in with the other one-pagers when I organize it. There's a table of values here, table of results. And I wonder if these end up in a book or something at some point. Like, I wonder where this data eventually gets used, if anywhere. Also, there's some water damage on this. Like, not from my household, but, like, there's actual... I could see where there was water spilled on this in the middle in its lifetime when it lived with Jerry, or maybe after. It's doing fine. There's, like, hardly any staining or any damage. I could just kind of see it where it's, like the paper itself is a little warped. There's a tiny bit of stain, like, right around the edge. But really impressed with how the paper survived. It hasn't like fallen apart at all over that. It's really good quality paper. Let's see. I'm gonna put this over here. These are things that have been stapled up in the corner like this. Just gonna put them all together. Here's another one right here. It's like a one-pager that's all the same size, all the same format. Just gonna put all that together. Maybe that will make it make more sense. Now this is kind of like that, except it's actually saddle stitched, aka stapled. And of course the thing with staples is that whenever they get super old, they look super nasty. They get really, really rusty over time. So part of the preservation of these documents may involve removing staples. We'll see. I'm not making any changes until I get some advisement on it. I'll read this one out. I think it'll be the last one for this video. Chemical Physics Letters 1, 1967, 429 through 433, North Holland Publishing Company, Amsterdam. Wave Operator Perturbation Theory for Intermolecular Interactions, a Test on H+2. You can see there how they write that, H+2. It's kind of hard to describe verbally. Ad van der Avoord. Oh, he was earlier. That name's from earlier. I recognize it. Unilever Research Laboratory of Lardingen, the Netherlands. Yeah, that's where he was on sabbatical from. And Battelle Institute Advanced Studies Center, Geneva, Switzerland. Yep, that's where he was at. In 1967, I think might have been the same year. The first order function and the second order energy of a perturbation theory proposed by the present author are evaluated for H2 by means of a Hilarious variation principle adapted to this theory. It is found that thus a considerable improvement of the wave function and the energy respectively is obtained. The importance of second order exchange forces is observed. The unsold approximation for the second order energy is tested. So that's what the front of this looks like. And I wonder how much of this is similar to, say, like Fourier transforms, which I learned about recently, like Fourier transforms and fast Fourier transforms. And those actually are equations to analyze data, separate it out, and find the waves within. Interatomic distance. Interaction energy. That's the different poles of this chart here. There's some citations. And there's another page back here with a little bit more data. Another table. And then the back is blank. So that's the last one here. December 1967 is when this is from. It was a different world. So hope you enjoyed the math. If you want to see more of these, don't worry. If you subscribe, you will see whenever I post them anytime, because I have a lot of them, and there will be a lot of posts because, oh my gosh, how much math can you fit into one article? We'll try having 300 of them. Look forward to it. Cheers.